You ever stop and think about what's really happening when you press a button on your phone or your TV remote? I mean, it feels instant, right? But underneath that simple click is this incredible conversation happening between you and the machine. Today, we're going to pull back the curtain and look at how our devices actually listen, and just as important, how they speak back. So let's just dive right in with this one big question. How does a device take a simple physical push of a button and turn it into a digital command it can actually do something with? It's this wild journey from our physical world into the world of ones and zeros, and trust me, there's a lot more going on than you'd think.
All right, here's our game plan. We're going to start with the most basic electronic hello. Then we'll uncover a really weird physics problem that every button has. We'll see how engineers get around it, scale that idea up to a full keypad, and finally, look at how the machines answer us.
You know, every conversation has to start somewhere. And in the world of electronics, that first word, that first bit of information, comes from the simplest thing of all, a basic switch.
Okay, so what we're looking at here is how that switch talks to the brains of the operation, the microcontroller. It's actually pretty clever. See, when the switch is open, when you're not pressing it, this little thing called a pull-up resistor keeps the voltage high. The microcontroller sees that high voltage and reads it as a logical 1, which basically means off. But the second you press that button, you close the circuit, giving the electricity a super easy path to the ground. The voltage plummets to 0, and boom, the microcontroller sees that 0 and knows, okay, it's on. It's a perfect, clean, two-state signal.
And let me tell you, that little resistor, it is the unsung hero of this whole operation. Because without it, pressing that button would connect the power supply directly to the ground. That's called a short circuit, and that is a surefire way to fry your electronics. So this tiny, simple component is what makes the whole conversation safe and reliable.
But here's where things get a little messy. Even with this really nice, clean setup, there's a hidden problem that comes from the real physical world. And that problem is called the bounce.
You know, on a microscopic level, when you press a button, the two metal contacts inside don't just perfectly connect and stay there. Nope, they actually slam together and bounce off each other a few times before they finally settle. Now, to you and me, it's one press, but to a super fast microcontroller that can check the voltage millions of times a second, it looks like you've pressed the button a dozen times in a row. So the trick to fixing this is called debouncing.
The absolute best way to picture this is with a basketball. When you drop it, it doesn't just hit the floor and stop dead, right? Of course not. It bounces a couple of times, each one smaller than the last, until it finally settles. That is exactly what's happening inside a switch with the electrical signal, and our device has to be smart enough to ignore all those little bounces and just count the first thud.
Let's look at what happens when we don't fix this. This circuit here is designed to be a simple counter. You press the step button, one more LED lights up. Simple. But without debouncing, you'd give it one good firm press and suddenly 3, 4, maybe 5 lights turn on. I mean, that's not a counter, that's just chaos. So this problem has to be solved.
So, how do we teach our machine to only see that one single intentional press? Well, engineers have two main ways to solve this. They can either use hardware or they can use software.
The hardware way is pretty cool. It uses a physical component, usually a capacitor, that basically acts like a tiny shock absorber for the electricity. It physically smooths out those bouncy signals. The software approach is different. It's less about fixing the signal and more about teaching the microcontroller's brain to just be a little more patient. The code essentially says, hey, I know you see a bunch of signals coming in, but just pay attention to the first one and ignore everything else for a few milliseconds. The most straightforward software trick is just to make the program wait. It sees that first voltage drop, and then it literally just stops. It sits in a tiny loop for a fraction of a second, which is just enough time for the physical switch to stop bouncing around. Then, after that little pause, it checks again. Hey, is that button still being held down? If the answer is yes, then it says, okay, that was a real press. But here's the catch with that simple delay method. While that little bit of code is waiting, the microcontroller can't do anything else. It's just frozen, waiting. And as the source material points out, that is incredibly inefficient. Imagine if your computer froze for a split second every time you typed a letter. In a complex device, you just can't afford to waste that processor time. So, the smarter way to do this uses the microcontroller's built-in timers. This is so much more elegant. When the code sees the first flicker of a button press, it starts a super short countdown timer and then immediately goes back to doing all its other jobs. It doesn't just sit around. Once that timer hits 0, it sends a special signal called an interrupt. It's like an alarm clock for the processor that says, okay, time's up.
Now you can go back and check if that button is really being held down. It's multitasking at its best.
Okay, so we've totally mastered a single button. But what happens when you have a whole keypad, like on your phone or a remote control? How does it know if you pressed a 5 or a 9?
You might think that a keypad with 12 buttons would need at least 12 wires going into the processor. And honestly, that makes sense, but it's super inefficient. Instead, engineers use this really clever grid system, a matrix of rows and columns. This way, our 12 keypad only needs 7 wires, or pins, to connect, 4 for the rows and 3 for the columns.
So the way it figures out which key you pressed is by scanning this grid at lightning speed. First, it sends an active signal down just one row, let's say the top one. Then it immediately checks all 3 columns. Is it getting a signal back on any of them? If it gets a signal back on column 2 while row 1 is active, it knows you pressed the 2 key. If it doesn't find anything, it just shuts off that row, activates the next one down, and does the whole thing over again thousands of times a second. So the machine has listened. It's ignored the bounce, it's scanned the keypad, and it knows exactly what you want. Now, how does it talk back to you?
Probably the most iconic and simple way a machine can respond is with a 7-segment display. You know these. They're on your alarm clock, your microwave, your calculator. Those numbers are made up of just 7 little LED bars that can be turned on or off in different patterns to make any digit.
So how does the brain know which segments to light up to show you a 2 instead of an 8? It uses something called a lookup table, which is really just a cheat sheet for numbers. If it needs to display an 8, it looks up the code for 8, which is FE in this case, and that code tells it, hey, turn on all 7 segments. If it needs to show a 1, it looks up the code 0C, which only turns on those 2 segments on the right side. It's a super fast dictionary.
But of course, sometimes you need to say a lot more than just a number. And for that, we need something like an LCD screen. These are way more powerful because they can show you a whole range of letters, numbers, and symbols, which allows for much better communication.
Now, talking to an LCD is a bit more like sending a text message. The microcontroller sends a universal code for each letter, called ASCII. There's also this special pin that acts like a traffic cop, telling the screen, okay, this next piece of data is a letter to put on the screen, or this next one is a command, like clear the display. And to be even more efficient with wires, it often sends the code for a single character in 2 smaller chunks, one right after the other.
And there you have it. From a single, physically bouncing button to a full sentence appearing on a screen, we've kind of peeked behind the scenes at the invisible engineering that makes our daily digital conversations even possible. So the next time you type something, maybe just for a second, think about that incredible high-speed dance of hardware and software happening right under your fingertips. It makes you wonder, what other invisible marvels are we taking for granted every single day?